Okay, this is our summary for directional derivatives and gradients. Let's take a look at the definition of a gradient. So a gradient for a function of two variables is really a vector of partial derivatives. So the vector is a two-dimensional vector. It has a partial with respect to x in the first component and the partial with respect to y in the second component. And if need be, it would be evaluated at x naught, y naught. Doesn't have to be, but if it is at a particular point, then you evaluate it. Function for a function of three variables. The gradient for a function of three variables is going to be a three-dimensional vector. Again, it's a vector of partial derivatives, f sub x, the derivative with respect to x, the derivative with respect to y, and then the derivative with respect to z in the last component. So that's the definition of the gradient. That's pretty straightforward. Let's take a look at some properties of the gradients that we went over. The gradient of a function is a vector in the domain of the function. So if the function goes from R2 to R, a function of two variables, then your gradient is a two-dimensional vector that sits in the domain of your function. If your function is a function that starts from R3 to R, a function of three variables, then your vector, your gradient, is going to be a vector in three dimensions. Alright, so that's the first property. Property number two, gradients are perpendicular to level sets. In the case of R2, a function of two variables, your level sets are going to be curves in two dimensions. So your gradient here is a two-dimensional vector that is going to be perpendicular to a level curve, and the level curve is going to be at the z level, z naught, whatever z naught is, and then so you'll have a function of x and y. Okay, if your function is going from R3 to R, then your gradient is actually a three-dimensional vector that is going to be perpendicular to a level surface. So what we have here is a surface, a function of x, y, and z equal to a constant, and then that's your, so that you can think about that as your surface, and your gradient is perpendicular to a level surface. So that could lead to a tangent plane if we want, and so that in fact will give us property number three. So property number three, the gradient, because it has perpendicular properties, you can look at it as being able to find tangent planes. So in the first case, the surface is given as z is equal to f of x, y. Then your normal component at the point is going to be fx, the derivative with respect to x, the derivative with respect to y, and -1. So given that as your normal vector, you can write your equation of a tangent plane looking like this. Z is equal to the z value at the point x naught, y naught, so f of x naught, y naught, plus a derivative with respect to x, evaluate x naught, y naught, so that's kind of like the slope in the x direction, and then you have x minus x naught, and then f sub y, the derivative in the y direction, evaluated x naught, y naught times y minus y naught. And I'm realizing that maybe you've seen this formula where instead of x naught, y naught, you have ab, and it's essentially going to be the same thing. Now here's the more important aspect of things. The surface, if the surface is given implicitly as a surface with x, y, z equal to 0, equal to something else, if it was equal to a constant, you can bring the constant on the left hand side and then it'll be the same thing. But the point is that if you have like those ellipsoids, for example, the sphere, hyperboloids, those are all implicit functions. If we want the normal vector at the point x naught, y naught, z naught, then that normal vector is going to be given by the partial derivatives, the gradient. So the gradient is perpendicular to a level surface, and you can think about your implicit function as a level surface, and so you can look at the partial derivatives as a gradient. And so you can rewrite your tangent plane as the derivative with respect to x times x minus x naught plus the derivative with respect to y times y minus y naught, and then the derivative with respect to z times z minus z naught, and equal to 0. Okay, so you have yourself a gradient. Okay, now let's take a look at the directional derivative and its properties. The definition for the directional derivative is going to be given by this formula. Now, the direction that we want has to be made into a unit vector for you to be able to use it in a formula. So if u is a two-dimensional unit vector, then the derivative of f at the point P in the direction of u is going to be a scalar dot product. It's denoted by d sub u vector of f, and then if you need to evaluate x naught, y naught, or ab, and that is going to be given by the dot product of the gradient times that unit vector that's given by the direction. And here's a formula just expanded out, given by components, but you know, the dot product is going to be your main source of your formula. If you have a three-dimensional unit vector and f is some three-dimensional function or function going from R3 to R, and then you have the point Q, which is a point in space, then the directional derivative is going to be given by the same thing. It's the gradient dotted with a unit vector v. Now it's exactly the same formula as the one up above, except you're dotting, instead of dotting two-dimensional vectors, you're going to be dotting two three-dimensional vectors. Okay, and again we emphasize that you're looking at the direction as a unit vector. So some properties of the directional derivative. The directional derivative formula can be written as a cosine of something. Now it's a dot product between the gradient and a unit vector, so that would be the magnitude of the gradient times the magnitude of the unit vector times cosine of the angle between them, but the magnitude of the unit vector is 1, so we can just say that there's a 1 in between here. The second property, the function increases most rapidly if you're going in the direction of the gradient. So this is essentially one of the formulas or one of the properties of the gradient, and it's related to the directional derivative in this way, aside from the formula itself. So not only is the direction of fastest increase the gradient, but you can actually find the value of the fastest increase, and that value is going to be the magnitude of the gradient. So it was already proven that the maximum increase is when cosine of theta is 1. That's when theta is equal to 0, which means they're going in the same direction. So that maximizes when cosine theta is equal to 1, and therefore your directional derivative is actually just equal to the magnitude of the gradient times 1, which is given here. Now, going the opposite way, the direction of the fastest decrease is going to be in the opposite of the gradient. So the opposite direction from the gradient, and that magnitude or that actual directional derivative is going to be negative. All right, property number 4, the derivative in the direction that's perpendicular to the gradient is going to be equal to 0. So this is remember that the directional derivative is a dot product, and if your u and your gradient are perpendicular, then the dot product is going to be equal to 0. So that is pretty equivalent to the gradient being perpendicular to the level curve. And then our last formula, or our last property, gives us a slight shortcut. If you want the directional derivative in the direction in the I direction, then that's essentially just fx. So think about the I direction as 1, 0, and if you dot your gradient with 1, 0, if u, the unit vector here, the direction is 1, 0, then really that's 1 times f sub x and 0 times f sub y, which is really just going to be f sub x. Similarly, if you're going in the j direction, your directional derivative is just going to be f sub y. Okay, so that is a summary of the gradient and the directional derivative. We fit it in one page. It's dense, it's a lot of information, but let's take a look at it put to use with some examples. Alright, let's take a look at a two-dimensional example. Here we have a function z, if you want, or f of xy is equal to the square root of x times y. And then we have a point 8, 2, and 8, 2 is assumed to be on the surface. So if we want the z component, then we can just plug that in and find that out later. Let's take a look at the questions that they're asking here. They want us to find a derivative of f in the I direction. So just according to the properties, and to make things quick for us, we can actually use your directional derivative formula. But if you're going in a specific direction like the I direction, then remember that the directional derivative in one of the directions in the coordinate direction is just going to be the derivative with respect to x. So let's find the derivative of this with respect to x. Your f sub x is equal to so the derivative of xy with respect to x, so that's 1/2 x times y to the negative 1/2 times the derivative of x times y with respect to x, so that's just going to give us a y. So just to rewrite it, this is going to be y in the numerator and then 2 the square root of x y under a square root. So this is a 2 being multiplied. You can go farther and simplify this, and we might as well do it just to simplify it. We have 1 y to the 1 power and y to the 1/2 power, and so 1 minus 1/2 is going to be positive 1/2. So that's just going to be 1/2 on the outside and then the square root of y over x. Okay, so that is your f sub x, and so that is your derivative. Now we need to evaluate at the point. So what we want is d in the I direction of f evaluated at the p point, which is 8, 2. And so that's really just f sub x evaluated at 8, 2. So this is 1/2 the square root of x is the 8 and 2 is the y. So this is 1/4. The square root of 1/4 is 1/2. 1/2 times 1/2 is 1/4. So that's your derivative in the I direction. Alright. The next one, the derivative of p going in the direction of q. So it looks like for this one we actually need to identify, let's get some space going here. We need to identify the direction that we're looking for. So PQ is going to be a vector going from P to Q. So this is going to be head minus tail, 11 minus 8, comma, negative 2 minus 2. So this is going to be 3 comma negative 4, and this is a vector. This is going to be the direction that you want. Now remember that when you do the directional derivative, you want to make sure that you get a unit vector. So we need the magnitude of this vector PQ that we just found. So this is the square root of 9 plus 16, which is square root of 25, which is equal to 5. So our unit vector is going to be 3/5, comma, negative 4/5. So you just divide by the magnitude. So that's the first thing we want. We want now the gradient. So we have the derivative with respect to x here, and so let's find the derivative with respect to y, and that's going to be the same process, right? This looks like there's some symmetry going on there. So we have the same thing. We got 1/2 x times y negative 1/2. Now we take the derivative of the inside with respect to y, and then that'll give us an x. and so that's going to give us a 1/2. And then if you do that canceling with the square root business, then you'll have x over y instead of y over x. Okay, so those are the two things that we need for the gradient. Now we need to evaluate the gradient, where we need to evaluate the partial derivatives at 8, 2. We already did the x with respect to the derivative with respect to x evaluated at 8, 2. So let's take the derivative with respect to y evaluated at 8, 2. So that's a 1/2. And then the x is 8, the y is 2. So this is going to be a 4, and the square root of 4 is 2, and 1/2 times 2 is 1. So our gradient is going to be a vector. Now I can put these functions there, but you know, we already worked it out and we put 8, 2. So let me just fix this up a little bit. We want the gradient evaluated at 8, 2. So that is going to give us the first one, which is a 1/4, and then the second one that we found with respect to y is going to be 1. So this is your gradient. So finally, our directional derivative of the function in the direction of u that we just found, evaluated at 8, 2, is going to be the dot product of the gradient, which is 1/4, 1, dotted with the direction that we're looking for. So that's 3/5, negative 4/5. So that's going to give us 3 over 20. Oops, not a vector anymore. 3 over 20 plus, I guess this is a negative 4/5. So I suppose we find common denominators. You get negative 16. Negative 16 plus positive 3 is negative 13. So we got negative 13/20ths. So this is our result. And that's a derivative of f going in the direction of, at p going in the direction of q. Alright. They want us to find the maximum increase, the direction of maximum increase. So let me underline the word direction there. So the direction of maximum increase, and the direction of maximum increase is just the gradient. So let's get that written there. The gradient of f evaluated at 8, 2. We already did this, right? We got this to be 1/4, 1. So that's the first part. Now, what is the actual directional derivative? Let me do this in a slightly different color here. The actual directional derivative that we're looking for. So that's a directional derivative in the direction of the gradient. I'll just say use the gradient. Well, maybe I'll just say the gradient of the function evaluated at 8, 2. So this isn't the gradient, instead it's the magnitude of the gradient. So according to our formula from the previous page, this is the magnitude of the gradient evaluated at 8, 2. So that's the magnitude, square root of 1/4 squared plus 1 squared. So that's 1/16 plus 1. So that looks like it's probably going to be the square root of 17/16, or square root of 17 over 4. We'll just leave it like that. That's good. Okay, so this is the actual directional derivative, the derivative in the direction of the gradient, and the first part that we saw was the direction of maximum increase. So this is a vector, and then your other answer is a scalar. Okay. All right, last problem here for this. Is there a comma here? There probably shouldn't be a comma there. So the last problem is asking us to find a tangent plane to the surface at this given point. So remember that our gradient is 1 comma or 1/4 comma 1. So the normal, actually let's not deal with the normal vector, let's just remember that formula. It's going to be z is equal to, so what are the components here? We need f of a b, or f of x naught y naught, or let's just go ahead and put 8 comma 2 as it pertains to this problem, plus fx evaluated 8 comma 2, that's 1/4 by the way, x minus x naught, and x naught is equal to 8, that's the first component, plus fy evaluate 8 comma 2, which is 1 we found, and then y minus the second number here is 2. Alright, we have these values. Actually, we almost have all these values except what is f of 8 comma 2. So the function is a square root of x times y. So that's 16. Square root of 16 is 4. Alright, we have ourselves our values, components. So this is going to be z is equal to 4 plus, we got a 1/4, 8, oops, that's going to be an x minus 8, plus 1 times y minus 2. Okay, so that's it. Let us take a look at this function. This is the function f of xy. This is the square root of x times y. And let us take a look at the function that's given by the plane here, which was, what is it, 4 plus, and then let's put 1/4 in parentheses, and you're multiplying by x minus 8, plus 1 times y minus 2. So this is our tangent plane, and you can see that it is in fact tangent to that surface at that point. Alright. Okay, sounds good. Let us move on. We have an example here in 3 dimensions. So we have a function that looks like z, e to the z minus x times y times z. So that's a function of 3 variables, x, y, z. And then our given point is going to be given as a point in x, y, z. So let's find a derivative of f at the point P in the k direction. So if you remember, this was simply the derivative in the k direction of this function. It's denoted a little f in our summary of formulas. It was called capital F, but that's not a big deal. So I think we need to find the derivative of this thing with respect to z. That's the k direction, and that is going to be e to the z minus x times y. And so we need to evaluate this. Fz evaluated at this weird looking point, e squared over 2 negative comma negative e squared over 2 comma 4. And so I have e to the 4th minus x, that's negative e squared over 2, and then negative e squared over 2. That looks like it will be e to the 4th minus negative negative is a positive, so this stays negative, e to the 4th over 2. So, oh, that's 2 times 2 is 4, e to the 4th over 4. So this is going to be a 3/4 e to the 4th. Okay, So we have the derivative with respect to z, and this is going to be the derivative with respect to z, and this is going to be 3/4 e to the fourth. So that's the first part. Now we're given a different direction, the direction in the I plus j plus k direction. So we're going to need to go beyond our f sub z here. We need to find f sub x and f sub y as well. So the derivative with respect to x looks like it's going to be, okay, e to the z will go away, negative, and then x is the variable, so that's just yz. Okay, so we need to figure out f sub x evaluated at this weird point. Let's just call it p here. And then I need to put negative, and then the y is going to be negative e squared over 2 times, and then z is just 4, so that becomes a positive. This becomes a positive 2e squared, and then f sub y, we have f sub x, f sub y, and f sub z is already there. So with respect to y, it looks like the e to the z is gone again. We have negative x times z. And so f sub y evaluated at that point is probably going to be the same because x and y are the same. So I'm just going to put 2e squared. Alright, so to find a directional derivative, you need the gradient. So the gradient of f is going to be evaluated at the point P. So let's go ahead and put that point P without writing the point itself. I'll just put the symbol P here. And that is going to be, with respect to x, is 2e squared. With respect to y is also 2e squared. And then with respect to z, we got that to be 3/4 e to the fourth. Okay, now we want the unit vector in this direction. So u, well, this is going to be the magnitude of this is going to be equal to the square root of 1 squared plus 1 squared plus 1 squared, so that's just root 3. So u is going to be 1 over root 3 times 1 comma 1 comma 1. I guess that's a vector. And so instead of distributing, I'm going to leave it like that, and then consider maybe distributing later, if at all. Okay, so the directional derivative of f evaluated at p in the direction of u is going to be this dot product. So the dot product of f evaluated at p dotted with u. So what is that? This is 2e squared comma 2e squared comma 3/4 e to the fourth dotted with 1/3. I'm just going to put 1 over root 3, 1 over root 3, 1 over root 3, and then this is going to be 2 over root 3 plus 2 over root 3, so that's 4 over root 3 e squared, and then we have plus 3 over 4 root 3 in the bottom e to the fourth. And I don't think you can combine that, so I would leave it as that. Alright, let's keep going. The direction of fastest increase. The direction, remember, is just the gradient itself. So the gradient of f evaluated at p, we already got that. That's 2e squared comma 2e squared comma 3/4 e to the fourth. And then the directional derivative itself is going to be the magnitude of f. So that is going to be the magnitude. I don't think we figured out the magnitude yet, so let's see. It's square root of 2e squared squared plus 2e squared squared plus 3/4 e to the 4th squared. So this is going to be 4e to the 4th, and there's two of them, so that's a square root of 8e to the 4th. And then this one is going to be e to the 8th, and then we got 9/16. So 9/16 e to the 8th. Okay, not much you can do to simplify. Just leave it like that. Finally, they want the tangent plane. So let's go ahead and figure that out. The tangent plane. If you remember looking back at our summary, the tangent plane can be given by this formula. We got this formula here. So let's go ahead and set that up. We do have the derivative already. We do have the gradient already. So it's going to be essentially the gradient times the values. So this is going to be your f sub x, f sub y, f sub z. So it's going to be f sub x 2e squared, and then x minus, do you remember the x term? Negative e squared over 2 plus, and then you got the f sub y, which is 2e squared, and then this, remember, is in parentheses. So, and then y minus negative e squared over 2. We can simplify that in a minute. And then plus the z this time. The z is 3/4 e to the 4th. And then we're multiplying it by z minus the z component. I think was 4. It is equal to 4. And then that's it. Equal to 0. You can choose to solve for z if you want, or you can just leave it like this. You can also simplify if you want. But let's see how this will work out. So there's not much simplifying to do. You can make these positive, but that's about it, I think, in terms of getting an exact formula. Let's take a look at the graph. And if you remember back, this is the graph that we actually did one time in class, but if you take a look at this thing, we can consider that as if it was a level curve, f of x comma y comma z equal to e to the z minus x times y times z. And if you consider this as a level curve at when w is equal to 0, we can think about this as 0 equals e to the z minus x, y, z, and that is equivalent to saying e to the z is equal to x, y, z. Alright, so we can look at that as a surface, an implicit surface, implicitly defined function surface. So let's take a look at that surface here. This is a surface, and I got rid of that point over here. So this is the point that we're looking at up there, and let's define another implicit surface that should be our tangent plane, and we have a bunch of e functions in there. So let's see how that works out. So the first derivative was 2 times e squared, and then we're going to multiply that by x minus negative, so that became a plus, and then it was e squared divided by 2, I believe, and then plus essentially the same thing, 2 e squared times y minus, or y plus, and then we have e squared divided by 2. I think I put that in parentheses, so I'm going to be consistent. Divided by 2, and then we have a plus, and then the derivative with respect to z was 3/4 times e to the 4th power times z minus z naught, or z minus c, or whatever, which is equal to 4. And then let's set that equal to 0. Okay, so here is our tangent plane. Our tangent plane tangent to that surface. Okay, at that particular point. Okay, so that about wraps things up. We have we went through a 2-dimensional example and a three-dimensional example using the ideas from the gradient and some properties of the gradient and directional derivatives. Alright, so I hope these examples make sense, and I hope they would help you prepare for understanding this and getting it ready for the test. So good luck.